Okay, this background, let's quickly the next couple of hours we will basically look. I mean, we will try to get some background on some basic analog signal processing blocks, namely filters, right? So, right. So, filter is basically a frequency selective network, right? For example, this is omega, and this is the magnitude response of the filter transfer function. So, this for example is the characteristic of an ideal low pass filter, and many times in block diagrams you will see this drawn like this. Okay, it's basically saying that it is removing mid and high frequencies, and it's only letting the low frequencies to flow to get through. Okay, this on the other hand, omega c, this is mod h of j omega. So, this is called the pass band, and this is the stop. This is a ideal high pass filter. So, this is the pass band, and this is the stop. And the symbol for this in block diagrams often it cuts off low and mid frequencies, and therefore, that is how it is done. Okay. Then this is omega c1, this is omega c2. This is band pass. This is band stop. Does it make sense, people? Is that clear? Okay. So, of course, in reality, I mean, these are have abrupt changes in the magnitude response at the band edges, right? Whether it's a low pass or high pass or whatever, the cutoff is abrupt. So, in reality, such an abrupt cutoff cannot be realized with physical components, right? So, in practice, only an approximation is possible. So, as you keep increasing the order of the transfer function, you can expect to get a better approximation to the ideal, right. So, in this course, because it is an introductory course, basically we will only discuss first and second order low pass and band pass filters. And okay. So, first order so the transfer function h of s is nothing but 1 by 1 plus s by omega naught, right. And what is the magnitude of the transfer function? One by the magnitude of one plus basically whole square. And what about the phase? Minus tan inverse omega over omega. So, if I plot the magnitude, I get something like this. The magnitude is 1. At what? So, at omega equal to omega naught, what comment can you make about mod h of j omega? Is 1 by square root of 1 plus 1 is 1 by root 2, so which is 0.707. Okay. And so this is called 1 by root 2 is nothing but minus 3 dB, right. Why? 20 log 1 by root 2 is minus 3. Actually, it's minus 3.01. But okay, so basically omega naught is called the 3 dB bandwidth. Is that clear? Now, so what is the easiest way of realizing this transfer function? Well, we've all seen this before. this is VO, all right, and VO of S by Vi of S, which is the transfer function, is given by 1 by SC over 1 by SC plus R, which is 1 over 1 plus SCR, and therefore omega naught, the 3 dB bandwidth, is 1 by RC radians per second. Okay. So, one problem with this circuit has got two problems. One is that if you want to drive a load with this, for example, right. So, let us say this is your filter and you add a load. What happens? Well, why speculate when you can work it out? So, what happens with loading? This is Vi, this is R, this is C. Let us say you put some load RL. This is VO. So, what is VO of S by Vi of S? One over the impedance of this is nothing but RL times 1 over SC by RL plus 1 over SC, which is nothing but RL over 1 plus SC RL. So, the overall transfer function is nothing but RL over 1 plus SC RL divided by RL by 1 plus SC RL plus R, which is nothing but RL over 1 plus SC RL, because I am going to multiply the numerator and denominator by 1 plus SC RL. So, basically I get I get RL plus R times 1 plus SC RL. Therefore, this is nothing but RL by RL plus R divided by 1 plus SC RL divided by R by RL plus R. Okay. So, this is nothing but so the DC gain, which was earlier 1, has now become RL by RL plus R. Does it make intuitive sense? Why? At DC, what comment can we make about the capacitor? Capacitor is open. So, at DC the gain must be simply that due to the potential divider, which is basically RL by RL plus R. Okay. Now, what comment can we make about the bandwidth? It is, what is it now? So, this is, I mean, remember that this is nothing but SC times R parallel RL. So, this is nothing but 1 over R parallel RL times C. Okay. And so, this is basically and why does this make intuitive sense? Yeah. So, basically remember that so this is the denominator polynomial of the network, right, and the denominator polynomial is also called the characteristic polynomial. Right, and as the name suggests, the characteristic polynomial is characteristic of the network, right, and does not depend on where you apply the input and where you look at the output, right. So, basically so the characteristic polynomial, if you look at it, well, it should not depend on the input. So, if I set the input, if I de-energize the input, that means all the voltage sources must become 0 and all the current sources must become open circuit. Then you must get the, the denominator of this network will be exactly the same as, or the characteristic polynomial of this network is the same as the characteristic polynomial of the other network, correct. And so, when you look at this, R and RL appear in parallel, okay. And remember that, so therefore, the characteristic polynomial is a fundamental property of the network, and does not depend on where inputs are applied. And what comment can you make about the roots of the characteristic polynomial? What are they called? Polynomial are the poles of the network. Right. And since the characteristic polynomial does not depend on where the inputs are applied, it follows that the location of the poles is also independent of where you apply the inputs, correct. Okay. And for stability, poles must be in the left half S plane. Is that clear?